Good afternoon, everybody. I guess to start off, I will entertain any questions on these integrals that I left for you guys to do. There were 6 of them. There are 6 of them there. Does anybody have any questions on how to go about doing any of these 6 integrals?
Sir, can you do 22?
Yep. Okay, so 22, we're gonna have to use substitution, but it's not obvious. It's a little bit tricky because when you're choosing your expression for u, you don't actually see the derivative there. So this is a question that requires a little bit of manipulating the function in order to do the integration. It's definitely one of the tougher substitution problems. So you would start with letting u equal x minus 1, or sorry, x plus 1. Then take the derivative of that. So du by dx is 1, which means that du is equal to dx. So then if we go and try and substitute that, so now if I try and now make this integral in terms of u, I would get the integral of x over the square root of u times du. Right? Dx just becomes du. The square root of x plus 1 becomes the square root of u. But now I'm stuck with that x there. I can't have that x there. Everything has to be in terms of u. But what I can do is I can use that expression, this one, and rearrange that so that I indeed get an expression for u. So what do I mean by that? I mean that if I rearrange that x would just be equal to u minus 1. And so the integral then becomes the integral of u minus 1 divided by the square root of u du. Which you should be able to evaluate. So how do I evaluate that? I'm just going to move over here, over to the left. You can break that up and write it as 2 integrals. It's the integral of u over the square root of du minus the integral of 1 over the square root of u du. The first one just becomes, so square root of u is u to the half. So just over here, u divided by u to the 1/2 is u to the 1/2. So this becomes u to the 1/2 du minus the integral of u to the negative 1/2 du. And now you find the antiderivative. So what function has u to the 1/2 as its derivative? So this would be u add 1 to the 3/2 multiplied by 2/3. Subtract u to the 1/2 multiplied by 2 plus a constant And then the last thing is just to back substitute in what u is. So you would get 2/3 x plus 1 to the 3 over 2 minus 2 times x plus 1 to the 1/2 plus a constant. Not so obvious, the substitution. So when that's not so obvious, this is how you would go about doing it. Are there any issues with any of the other ones? Because some of the other ones you would have to do it's the same idea, right? So for instance, number 23, you would have to do number 23 sort of the same way. Your choice for u would be x minus 3. So does anybody want me to do one of these other ones? Do you want me to do 23 just so we kind of get the idea of what's happening here, or are we good with that?
Sir, can you do 23?
Yep. So again, substitution is not obvious because the derivative, like I would say, let's let u equal x minus 3, but the problem is that the derivative is just 1, which I don't see in the integrand. So we're going to have to do the same thing. We're going to have to rearrange this thing and get an expression for x, which means x would be equal to u plus 3. Okay, so I'm going to use this for x. X is equal to u plus 3. X minus 3 is just equal to u, and then dx is equal to du, and that would convert my integral into everything in terms of u. So my integral now would be u plus 3. Okay, that's my x, multiplied by the square root of u times du. Now, if you write u to the 1/2, write square root u as u to the 1/2, this becomes u plus 3 times u to the 1/2 du. And now just distribute that u to the 1/2 into the bracket. So that would become u to the 3 over 2 plus 3u to the 1/2 du. So now I just take the antiderivative of each one of these terms in the integrand. So there are 2 of them. I'll just move over here to the left. That would be u to the 5 over 2 divided by 5 over 2, which is the same as multiplying by 2/5. Plus 3 times u to the 3 over 2 divided by 3 over 2, which is the same as multiplying by 2/3. So when I multiply 3 by 2/3, I'm just left with 2 here, plus a constant. And so now when I back substitute, I would get 2/5 x minus 3 x minus 3 to the 5 over 2 plus 2 times x minus 3 to the 3 over 2 plus some constant. Any other ones? So 24 is done the same way. 25 you would have to do the same. They're all the rest of the 24, 25, and 26. You would have to do something similar to these last two problems I've just done. So I don't want to do them all. I think there's merit in you guys actually going to try this, but I can tell you that 24 is a substitution, and you're going to let u equal x plus 2. Okay, and then just follow what I did in those two examples. For 25, you would also, this one here, you would let u equal x plus 2. Okay, so given that, you can go and try and do these problems now, following the same method that I used for 22 and 23. And for 26, you would be letting u equal 2x minus 1. And again, follow the same kind of process I did for 22 and 23. So I would expect that some of you may have had issues with those. I encourage you strongly now to go back and try these given what I've shown you. There is another example that I did with you a while ago that's similar. When I introduced this method of substitution, it's the same idea as this one here, number 9. So there's another example you could look at. It's the same sort of idea as what we just did today. So if you go back and look at example 9, that's another example you could stare at. So please go back and try those ones there that I haven't done. And next class, if you're still struggling with it, I'll go through these ones as well. So before we leave this, is there any more questions that you want to ask regarding integration? Okay, so again, please go back and try those now that you get that I've demonstrated how you would do these. 24 and 25 and 26 are all done the same way. Which brings us to the next topic, which is posted here in OneNote. By the way, I don't know if you've noticed, but I forget to mention this all the time, but I've posted all these kind of notes that I go through with you. They're all posted. I've been posting them in EDSB in the library under Unit 4. So if you go look in the EDSB library under Unit 4 and you want to print these things out for yourself, you can do that. And I will continue to post them. For those of you that like me to post them, and if I do forget, please just remind me, and I will post them in the library in EDSB so that you can print them out, and maybe you'd like to write them in your own notes as we go through this. So last class, did we finish this? Area approximation methods?
I think we had to go through the last 3 examples.
1, 2. Okay. So we had the swimming pool. Let's do that. Let's start with that. And so you have a rectangular swimming pool, 30 feet wide and 50 feet long, and there's a table of values here that gives you the depth of the swimming pool at 5-foot increments as you move along the length of the pool. So starting at 0 all the way to 50 by 5-foot increments, it gives you the depth. So the depth at 0 is 6 feet. The depth at 5 is 8.2 feet. And you can see what I've begun to do there on the left is construct a cross-sectional view of the swimming pool. So what we need to do is we're going to estimate the volume by calculating that cross-sectional area all the way from 0 to 50. And if we take that area and multiply it by the width of the pool, which is 30, that will give us the volume of the water in the pool. Okay, so in part A, I used LRAM. So I'm just using the rectangles there that are in that cross-sectional profile. So the width of every rectangle is 5. So I've highlighted there inside the large square bracket. That 5 is just the width of every one of the rectangles. And all the other numbers are the heights of the rectangles, keeping in mind that we're using LRAM. So our first height, in this case they're actually a depth, would be 6, and then 8.2, 9.1, and I continue all the way through the table up to 12.7. Okay, so that highlighted term there is just the sum of all the rectangles that are in that cross-sectional area of the swimming pool. Then I would take that and I'd have to multiply it by 30 because the width of the pool is 30. And when I do that, you get 13,965 cubic feet. Part B is the exact same thing. The only difference is you're using a right rectangular approximation. So the width of the rectangles are still 5. Except now if we're using a right rectangular approximation, I would start at 8.2, then 9.1, 9.9, 10.5, all the way down to the end. So this time I would be using the last value in the table, but I wouldn't be using the first value in the table.
Sir,
Yeah?
for A, I got a different answer.
What?
Like, I did the exact same thing, but when you type it into the calculator, you don't get that.
You're lying. It's definitely that. So do you not get 465.5?
No.
Okay, so hold on. Maybe I'm wrong. The 13,965, did you get that?
No.
What is it? Throw the calculator out then. Okay, anyone else who's interested in verifying this? So I have my calculator. I'm going to do this again. But you guys should try this too. 6 plus 8.2 plus 9.1.
Sir, I got your answer for A.
Uh-huh.
I didn't get it for B, though.
Oh, geez. Okay, well.
I didn't get your answer for A. I have the same as Sierra.
Yeah, I'm with Sierra and Cash. I did not get your answer for A or B.
Okay, now I'm not getting it either. What did you get? 515.5?
Yeah.
What? Where's the mistake? Okay, I'm not getting that anymore either. I'm getting 30 times 515.5, which is 15,465. Anybody get that?
Yeah.
Yeah, I got that.
Yeah, I got that.
Okay. So is my B answer wrong as well?
Yeah, I got something different for B, sir.
Okay, good. So let me see what I get, and then I'll see if we're all on the same page again. Okay, so 5 times. What did you get?
I got 16,515.
I'm getting the same answer for this one.
Okay, then maybe I'm wrong.
Is anybody else getting 500.5?
Sir, I got the same as Lori.
Yeah, I got the same as Lori too.
I'm confused. Okay, so this is 550.5, correct? Does that make more sense? Let's see. Times 30. 16,515.
Yeah, that's what I got.
Okay, let me change that. 16,515. So it's a good thing you guys did that. I appreciate it. So let's fix this. I don't know why I'm getting different answers all the time. All that is a puzzle to me. 515.5. And that means this is 15,465. Now, does everyone agree with those two answers?
Yeah.
We're good with those?
Yeah, we're good with those.
So 15,465 and 16,515. Oh. Okay. So, estimate the volume of water in the pool using the trapezoidal approximation. So this calculation here must be wrong as well. Okay. Because if I take the shortcut, I should be able to average those two numbers to get the trapezoidal approximation, right? 15,465 plus 16,515 gives me 15,990. Is that what you guys got?
Yeah.
Okay. Which means that something is wrong with my calculation here. This can't be right. Correct? This number here should be 15,990. So what have I done wrong there? Have I forgotten a number? Yes, I did forget a number. That's why. So missing from my calculation here, I can see right away, I should have here plus 2 times 9.9. I missed that one. Where do they find these people? Where do they hire these people at Villanova? It's unbelievable. 9, 2 times 12.3. Okay, that should be correct now. This is wrong. Bear with me, folks. So what is that number in the bracket? Does anybody know?
I know that 5/2 times the number in the bracket is 553, but I didn't solve for the number in the bracket.
$221.2. Let's see. 221.2 times 5 divided by 2.
Sir, I got 213.2.
Holy crap.
I got the same as Sierra. I got 213.2.
213.2. Let's see. Yes, that would be right. And then that would make this 15,990. Which it should. It has to be 15,990. Everybody okay now? No? I didn't get 213.2, but I don't know what I screwed up. But that is right. Oh, hold on. Yes, that is in fact correct. 213.2 is correct, and 15,990 is correct, and now we're good. So we've got our LRAM is 15,465, RRAM is 16,515, and the trapezoid is 15,990. And that can all be verified over here by using the shortcut. And so that's it. So thank you guys for catching my mistakes. Any other questions on this one? So that is now correct. I forgot this term in here, which I've now added, so it all works out the way it should. Next question. Oil leaking out of a tanker damaged at sea. the damage to the tanker is worsening as evidenced by the increased leakage each hour recorded in the table below. So we've got a rate in gallons per hour, and we've got that rate at a bunch of times from 0 to 8. Part A is asking to estimate the amount of oil that has escaped in the first 5 hours using LRAM and RRAM. So the width of each rectangle is just 1, and if I'm using LRAM, it's 50 plus 70 plus 97 plus 136 plus 190, and that would be 543 gallons. Everybody concur with that? Maybe.
That's good.
And then RRAM is the same thing. 1 times it now. Since you're using RRAM, it's 70 plus 97 plus 136 plus 190 plus 265. And I hope that's 758 gallons. Okay, again, the units are important. You're taking a gallons per hour for each rectangle and multiplying it by the units of hours. So the hours cancel each other out, and your units left would be gallons. So 758 gallons. Part B says estimate the amount of oil that has escaped over the entire 8-hour period using a trapezoidal approximation. So I cheated here. I found LRAM and RRAM. And the reason I did that is because all I have to do is find the average of those two numbers, and that will give me the trapezoidal approximation. So this is what I was referring to last class, is that if you're asked for a trapezoidal approximation, there's no reason why you couldn't do what I did. So, are those numbers correct? Did anybody get something different?
I got the same.
Okay, good. So that's just a short. In my mind, it's easier just to do LRAM and RRAM and do the average of the two. Now, if you actually did the trapezoidal calculation, you should get exactly that number, 2,028 gallons. It's just a lot more work. Okay, the last one. What's different about this last one is that the rate that we're given, so the graph represents the volume of how the volume of water in a tank is changing over a 16-minute period of time. So the rate is a volume per unit time. So when you multiply that by units of time, again, you're going to be left with just volume. So part A, the area under the graph from 0 to 8 using RRAM is 140 liters, and that represents water added to the tank from 0 to 8. And I'm assuming that calculation is correct. Please stop me if they're wrong, and we'll go back and do it over. Part B, find the area under the graph from 8 to 16 using right rectangular approximation, again with 8 subintervals. So when you do that, the area is 80. Keep in mind, folks, that area is a positive quantity. Even though we're below the axis, the actual area of that green triangle is 80. It's just that the interpretation is different. It's because those rates are negative that the interpretation is that the volume of that 80 liters of water is being removed from the tank. That's what a negative rate would indicate in this problem that water is being removed from the tank. So the area of that green triangle is 80, which represents 80 liters of water being removed from the tank. So the net change in volume, you just subtract the numbers. Or 140 that you added and 80 that you've taken out would give you 60 liters of water would be the net change. So over 16 minutes, 60 liters of water would be added to the tank. That would be the net result. Any questions on that? Okay, then this is just to summarize. And again, what it's summarizing is that you can think of adding up rectangles or trapezoids as you move from left to right. As you add up those rectangles or trapezoids, you're accumulating area. Okay? The accumulation of the area under a rate of change, and you can think of that as a derivative. The accumulation of that area of a rate of change of some quantity would give you the net accumulation of that quantity. And that's exactly what the last example was demonstrating. So the area under a volume per unit time versus time graph would give you the net change in volume. The area under a velocity versus time graph would give you the net change in position. Okay, remembering that velocity, the definition of velocity is the rate of change of position. And finally, the area under the rate of change of any quantity Q versus time would give you the net change in that quantity Q. So that last one, this last statement, is just the generalization of the first two specific examples. So if you have any rate of change of some quantity Q and you find the area under that graph, it'll give you the net change in Q. That's what that statement is saying. Any questions on that? Okay, so that brings us to the next topic here that I've got, area and definite integrals. The whole point of this lesson here is as follows. We started off today with integrating. How do I find antiderivatives? Okay, we talked about substitution, we talked about completing the square, we talked about those methods of finding antiderivatives. And then after that, the lesson we just talked about was area under rate of change graphs. This lesson connects the two. So how is finding antiderivatives, or how is integration related to the area under a graph? That's what today's lesson is about, and we're not going to get through it all because we've spent half the day fixing my mistakes. But we'll start anyways, okay? How is the area under a graph related to integration? That's what today is about. So, first example. And it's important to note that in this example, the function f of x is positive on the interval in question. So in this question, we're given this graph, f of x equals 5, and we're interested in that function on the interval from 0 to 10. So you can see from the red line there that the y values of the entire function are positive. Okay, there is no part of this graph that's below the x-axis. Calculate the area under the graph of f of x over the interval from 0 to 10. So we don't need to use RRAM or LRAM. It's just a rectangle, right? We're looking for the area under this graph from 0 to 10. So that area is equal to 5 multiplied by 10, which is 50. Okay, I've left out units. We're not really interested in units. In the context of a problem like we did, like those last examples with the volume in a tank, yes, the units are important, but for the purposes of this lesson, we're not using any units. So the area under that graph is 50. Part B says determine capital F of x, which is just the integral of little f of x. In other words, we're finding the antiderivative of little f. So we need the integral of 5, f of x is 5 dx, and that would be 5x plus some constant. So capital F of x is just 5x plus a constant. So that you might be thinking random, what the hell does that have to do with the area? So part C, determine that antiderivative at 10 when x is 10. Why am I choosing 10? That's not a random choice. 10 is our endpoint here. And you can see in part D it says find capital F at 0. That's our starting point. Okay? X extends, we're interested in the interval x equals 0 to 10. So capital F at 10 is 5 times 10 plus a constant. So that's 50 plus some constant. And right now I don't know what the constant is, but we're going to see that that won't matter. Now I do the same thing. I take my antiderivative, 5x plus c, and I sub in 0. And I get 0 plus c, or I just get c. Now I'm going to take those two expressions, this f at 10, which is 50 plus c, and f at 0, which is c, and subtract the two. So f at 10, subtract 0 would be 50 plus c, subtract c, which gives me 50. And you can see that the c was irrelevant. It didn't come into play at all. But the important thing to notice here is that that expression, f at 10, capital F at 10 minus f at 0 is 50, is the same as the area under the graph. That's the important point. Now, is it random? Does it always happen? Or does it just happen in this example? Well, let's try it. This was a fairly straightforward example, and I picked that because it's very easy just to integrate the function 5. Let's try something else and see if it works again. So the next example, okay? Again, f is positive. So all the y values of that function x plus 2 are positive. And we're only interested in the interval from -1, so from here to 5. And you can see we've got that shape there. It's a trapezoid. But part A, we're going to do the exact same thing again. We're going to calculate the area under that graph and compare it to what we get after we find the antiderivative and evaluate it at the endpoints of the interval -1 and 5. So this area, you may want to, there's more than one way to calculate this area, but you may want to split it up into a triangle and a rectangle. So I'll do that. That's equal to 6 is the area of the rectangle plus, what do we got? The area of the triangle. Half of 6 times the height of 1, 2, 3, 4. 1, 2, 3, 4. 6 again. Gives us what? $24. So this entire shaded region here, that has an area of 6, and then the triangle has an area of 18, and when you add those two together, you get 24. Everyone agree with that? Capital F, the antiderivative of our function, is the integral of x plus 2 dx. So, now I need to find the antiderivative of x plus 2. That is x squared over 2 plus 2x plus a constant. That's the antiderivative, the integral of our function. Now, f at 5. F at 5. So I'm evaluating my integral at the endpoint 5. That's equal to 5 squared over 2 plus 2 times 5 plus a constant. What does that give us? 22.5 plus a constant. F at -1 is -1 squared over 2 plus 2 times -1 plus a constant. What does that give us? I believe it gives us -1.5 plus a constant. Now subtract the two things. So f at 5 was 22.5 plus a constant. Subtract -1.5 plus a constant. We get 22.5 plus c plus 1.5 minus c. And you can see that the c's cancel out. Again, the c's are irrelevant. And we get 24. Which is exactly the same as the area under the graph. So it looks like it's not completely random, that this happens all the time. And we can try it again. Let's see what happens now if f of x is negative. So the third example, we've got y equals 2x minus 4 on the interval from 0 to 2. Calculate the area under the graph. So that's just a triangle. Now, we're being asked to calculate the area. So area is never a negative quantity. It makes no sense to say that the area of your living room is negative, whatever, 1,500 square feet. Area is a positive quantity. So this is 1/2. The base, which is 2, times a height, which is 4, gives us 4. So the area is 4. This area in here is 4. So let's determine the antiderivative of f of x. That's equal to the integral of 2x minus 4 dx. That would be x squared minus 4x plus a constant. evaluate that antiderivative or that integral at the endpoints. So f at 2 is 2 squared minus 4 times 2 plus a constant, which is 4 minus 8 plus c, which is negative 4 plus a constant. F at 0 is 0 squared minus 4 times 0 plus a constant, which is c. F at 2 minus f at 0 is negative 4 plus c, subtract c, which is negative 4. So now we have this negative sign here. When we compare f at 2 minus f at 0 with the area, you can see that the value is the negative of the area. That will always happen when you're dealing with a function which has y values that are negative. So when you find the antiderivative and evaluate it at the two endpoints, when the function is negative, it will give you the negative of the area. Okay, so that's just something to keep in mind. When the y values are negative, the area, or the integral evaluated at the endpoints, is the negative of the area. Okay, and I think I will stop there. And we will pick up next class with this example. Let me just put an asterisk here beside it. We'll pick up here. So what happens when you have both a positive, the function has parts that are both positive y values and negative y values? What would happen in that case?